Okay, in this video, I'm going to go over some of the lab calculations. So this is something you might see on tomorrow's quiz. If you're given this information, and in case you can't read the numbers here, the mass of magnesium is 0.0409 grams, gas collected is 43.9 milliliters, room temp is 23.0 degrees, barometer reads 758 millimeters mercury, and the vapor pressure at 23 degrees, which is looked up, is 21.0. So the types of questions you should be able to answer from this: how many moles of gas were produced? What was the partial pressure of the H2 gas? What would this gas's volume be at STP? And based on this data, what is the volume of 1 mole of any gas at STP? So in fact, if you want to pause this and try working through these, that might be a good idea. But let's start working through them now. So first of all, how many moles of gas were produced? Well, I know grams of magnesium, so let's write out this equation here. So magnesium is going to react with HCl, single replacement reaction. Magnesium is going to try to bump hydrogen, and it can. So we're going to get magnesium chloride plus hydrogen, which gets bumped, but because it's a Brinkelhoff, that is of course my H2, and this is my gas. To balance this equation, we say 2 of these, and the rest is good. So it's a 1-to-1 ratio. So therefore, I gave you grams of magnesium. We're going to convert grams to moles, look at our mole ratio of 1-to-1, and pull out moles of hydrogen gas. So 0.0409 grams divided by the molar mass of magnesium, 24.305, gives me 0.00168 moles of magnesium. 1-to-1 tells me this is exactly the same number of moles of H2 gas. Question number 1 is done. Question number 2, what was the partial pressure of the H2 gas? Okay, so remember that when we ran this through the water, let's say this was your water, or I mean it's really dilute HCl, and let's say this was your gas. So this was mostly H2, but there was also a little bit of H2O in there. Now the total pressure is equalized with the room. So the pressure total equals the pressure in the room, which was what the barometer read, 258 mmHg. Not 258, 758. Okay? And this total pressure is the sum of the two partial pressures. Now I gave you the partial pressure of water, 21, so therefore the partial pressure of hydrogen gas is just this minus 21. So 758 equals my pressure of H2O plus my pressure of H2. Well, since I know that this is 21, solve and we get, what's that going to be, 737. pH2 equals 737 millimeters mercury. Okay? Question 3. What would this gas's volume be at STP? And by this gases, I'm referring to the gas that we collected, because we didn't collect it at STP. So, here's my pressure. Here's my temperature, because we're assuming, this is an assumption, we're assuming that the gas had the same temperature as the room and as the water. And let's see, my volume is this. By the way, you might wonder, well, hold on, if this gas contains H2O and H2, don't we have to subtract the volume of the water? Well, no, because any gas fills any container. So these gases have the same volume but different partial pressures. Okay? So we know our volume, we know our temperature, and we know our pressure at room conditions. What we want to do is say, well, if we tweaked the pressure and we tweaked the temperature to get them to STP, what would the new volume be? So anytime we kind of adjust conditions and see what the change is going to be, combined gas law. So P1 V1 over T1 equals P2V2 over T2. So let's rearrange and solve for what I'm looking for. The question says, what would this gas's volume be at STP? Therefore, we're solving for the new volume, or V2. V2 equals, okay, so I always rearrange first. So it equals P1 V1, okay? Then it's going to be multiplied by this, so that's going to go up here. So times T2, okay? Divided by, this is already down here, T1. And this P2 is going to be divided by P2 here. So that is our equation. Let's plug in our values. Pressure 1, 737 mmHg. It's important that we don't accidentally put 758 because that is too high. That is the pressure exerted by both gases. So 737, make sure that's right, yep, millimeters mercury. V1, 43.9 milliliters. You might be saying, wait, don't we have to convert this to ATM? Don't we have to convert that to liters? Well, no, that's only for the ideal gas law. In the combined gas law, whatever units you put in are the units you're going to get out, and it works. The only thing you have to do is convert temperature to Kelvin, which I'm going to do right now. So temperature 2 is what the temperature would be at STP, 273 Kelvin, divided by, let me just double check. See? This is why I double check. Okay, V2. I'm solving for, no, I am right. It's going to be T2 up there. Okay. I don't know why I'm thinking it's going to be different. Anyway, let's plug in our values here. Yes. Sorry for the confusion. T1. 23 degrees Celsius, which we need to convert to Kelvin. 23.0, technically we're going to add the 0.0 here, so we're going to say 273.15, which is going to give us this, and technically since we have one number past a decimal point of precision, we're going to round that up to 2, so we're going to say 296.2 Kelvin. And pressure 2 is what the pressure would be at STP, which is 1 atm, but in this case, since I gave you mmHg here, we're going to go 760 mmHg. And this entire thing equals V2. Let's check our units. Millimeters mercury, Kelvin, Kelvin, milliliters is my unit. Let's plug the numbers in. Okay, 373 times 43.9 times 273 divided by 296.2 divided by 760 equals, and looking at sig figs here, this we assume is infinite because 760 is just accepted as standard pressure. So all the rest give me 3 sig figs, so I'm going to call it 39.2 milliliters. And comparing that to the volume I got, in this case it makes sense. We collected 43.9 milliliters. And I'm saying if we were at a CP, it'd be a little bit less. And think about it, we're pretty close to standard pressure. I mean, if you're off by standard pressure by more than like 10%, you're going to feel it. You're going to either throw up or you're going to like fall on the ground and crumple up into a little ball. And, you know, we're somewhat close to standard temperature, but in order to get to standard temperature, you need to drop it down to 0. So really pressure is going to be the same, but we would drop the temperature by like 23 degrees Celsius. And when you decrease the temperature, the gases are going to kind of start condensing a little bit, and it's going to shrink. So it makes sense that it's a little bit less. So that's my answer for this problem. Step 4. Based on this data, what is the volume of 1 mole at STP, which is the whole point of this lab? So what we found was that our gas sample had a volume of 39.2 milliliters. But that wasn't 1 mole. We found the moles, and it was right here. So that was 0.00168. Okay, so this many moles occupied that much volume. We want to see what the volume would be at 1 mole. Now you could also, in lieu of this, you could just do this divided by that, which would turn that into 1, which would get you your answer anyway. But doing it this way, cross-multiplying 39 times that, so it's going to be 39.2 divided by 0.00168. And I got 23,333.3 repeating forever, but of course with sig figs, we're going to go 23,300, and my unit here is milliliters per mole. Okay, and you can also call this 23.3 liters per mole. And that's pretty close to the actual value, which is 22.4. So, I could also ask you a percent error calculation. So for this, you would find the difference divided by the actual, or the theoretical, and you'd get your percent yield, or percent error. Okay, so this is the type of calculation you're going to do for tomorrow. Keep in mind, if you're watching from period 5, you're going to have that quick 5-question kind of supplement. I'm going to ask the combined gas law, the ideal gas constant, the conditions for STP, and the volume of 1 mole of gas at STP.